Morning, everybody. Hello, my name is Zia Lennard from R2M Solution, and I will be chairing this energy storage paper session this morning. We'll be going from 9 o'clock to 10 o'clock, and we have two very high quality presentations for you. First up, we have the role of storage systems in industrial and residential environments, and that'll be presented by Andreas Tuerk and Camilla Neumann and Joanna Puker from Joanneum Research. Joanneum Research, excuse me. And then after that will be Adriano Sciacovelli, I hope I pronounced that correctly, from the University of Birmingham. And he will present kinetic modeling of thermochemical energy storage reactions for storage of solar heat. So without further ado, well, please enter your questions into the question pane and I'll make sure that they go to the correct speaker. And without further ado, we will pass it over to the Joanneum Research crew. Take it away.
Good morning. My name is Andreas Tuerk, Joanneum Research, Austria, Graz. I will give the presentation together with Camilla Neumann and Johanna Puker. And the presentation is called The Role of Storage System in Industrial and Residential Environments. Next. The results stem from the Horizon 2020 project Story. Story was a 5.5 years project and is ending end of October. The goal was to assess the added value of storage in distribution grids for sorry, we have to fix something. Sorry. Nicht eben nachlassen. Passt. The goal was added value of storage in distribution systems for flexible and secure energy system. The project started already in May 2015 and is ending now with a budget of 15.8 million euro, 18 partners from 8 countries, 6 different demonstrations in 4 countries, with a diversity of technologies and actors, ranging from TRL 5 to 7. An important question was the interoperability in ICT. We assessed per demo economic, social, environmental effects. We assessed also the effects in the context of large-scale simulations. Finally, we developed innovative business models. Today, we would like to give you insights in our economic, social, environmental assessments. Let's have a look at the demos. We had residential demos, we had industrial settings, as I mentioned, a diversity of technologies. In one demo in Belgium, we had an aggregation of residential flexibilities and a community battery in a neighborhood with 13 houses, heat pumps, EVs, fuel cell, thermal storage, and a neighborhood battery. Then we had in Spain a lithium-ion battery, 50 kilowatts in a factory to improve the business case. There was already quite some PV in the factory, and the battery was added. Then we had another demo in Belgium focusing on thermal storage. A wood processing factory had already an old biomass boiler, but they installed a new boiler with an organic Rankine cycle system and adding a thermal storage to improve the heat supply and possibly also to supply neighbors with heat while the ORC is producing electricity. With another demo, a small-scale compressed air energy storage system in North Island. The idea was to reduce wind and PV curtailment. And you know, there are some compressed air energy storage projects in Europe. Normally, they need a big underground cavern to store the compressed air. Here we wanted to develop a small-scale system where the air is stored in cylinders that you can replicate in many locations. Unfortunately, the TL level was too low and we had to stop this demo. Finally, we had a community battery in a residential village in Slovenia, tested by a DSO. The DSO wanted to know which services and which benefits would a community battery bring in a grid that has possible limitations at higher PV levels. We zoom now into 3 of the demos. The Spanish demo, storage in the factory, the demo in Belgium with our sea and thermal storage, and the community battery in Slovenia. This is a bit the narrative of our presentation. First, we will present you large-scale simulation results that represent a typical European network with good grid conditions. But then we will contrast the results with demo cases representing real-world constraints. And finally, we will compare simulations with demos while assessing demos from an environmental, technical, and economic viewpoints. We would like to understand, does storage always make sense? And under which conditions do we find a business model and an good environmental beneficial outcome? Because from a governmental perspective, you want to decarbonize, you want to deploy technologies that lead to decarbonization. From an investor perspective, you want to deploy systems that have a business model. And there may be possible trade-offs that are often maybe not well understood and forgotten. Next slide. We start with the result of the large-scale simulations and hand over to Johanna Pucker, who will give some insights here.
Yes, the large-scale simulations are based on a medium voltage network with rural and urban grid sections. And in this simulation, different scenarios were investigated, where different parameters are changed in each scenario. So the first thing which was changed in the scenarios or investigated in the scenarios was the amount of PV units installed in this grid section. So we had scenarios with, let's call it to be a little bit more simple, with a low amount of PV, and we had scenarios with a high amount of PV installed. And which was also investigated was different type of battery storage systems. So we had scenarios where battery storage systems were implemented in households, and we had systems or scenarios where battery storage systems were implemented in at the transformer station directly in the power grid, which is based on one of the demonstration cases Andreas already presented. And we also changed the amount of battery storage systems or the amount of power of battery storage system installed in the scenarios. So we had scenarios with a low amount of batteries, with a medium amount of batteries, and with a high amount of batteries. And the main focus on these simulations were technical results. But what we also did, we did an environmental impact assessment using life cycle assessment to investigate these different scenarios and to figure out what is the role of the battery, how do the results change if we implement these different battery storage systems in the scenarios.
I want to make one addition. Okay. So the simulations were carried out by the University of Ljubljana, and we did the environmental assessment.
Yes, that's true. So the technical simulations are the basis, are the basis for the results, also for the environmental analysis. So here you see the results from the life cycle assessment. It shows greenhouse gas emissions per megawatt electricity demand in the investigated grid section. And on the top, you see 3 green bars showing the scenarios with a low amount of PV installed. The first one on the top is the scenario where we have no battery. The second one, here we installed a low amount of batteries on household level. And the third one, a medium amount of batteries on household level. And what you can see here is that the the specific greenhouse gas emissions are very similar in those three cases. So installing the household batteries here led to a small increase in greenhouse gas emissions, basically because the battery system had storage losses, and these storage losses increased the greenhouse gas emissions of the system. At the second set of scenarios, we have a really high PV penetration. The first blue bar shows the scenario with no battery, and below that, different scenarios where we installed the battery at grid level, and again, we had batteries on household level. And what you see here, that especially in the scenarios with the battery installed on the grid level, the greenhouse gas emissions are increased to the battery. A minor influence are the greenhouse gas emissions for the battery manufacturing, but that is not the main point for the increased greenhouse gas emissions. The major contribution are storage losses due to the battery storage process, but also we figured out that here we use data from our demonstration case that this battery storage system installed next to the transformer station is put into a container. It's standing outside. It's summer and winter the whole year, and it needs heating and cooling. And this amount of energy used for heating and cooling is rather high and adds also additional emissions to the scenarios. What also happened here is that, as Andreas also mentioned, the grid we investigated had really good conditions. It showed on a technical side very few limitations through the high amount of PV, so it was able to transport the PV electricity through different grid levels. So the PV electricity was not curtailed. It could be used in all scenarios. And this also led to the fact that the battery increased the greenhouse gas emission in this setting with good grid conditions.
Thanks, Johanna, for this assessment of the large-scale simulations, concluding that batteries can increase emissions. But now we zoom into the demos. We start with a demo case storage in a factory in Spain. Camilla, give us some insights.
Yeah. This factory produces professional fridge rooms, and due to the constant turning off and on of the machinery, they produce quite high power peak values. And before the project story started, they had already installed a 113 kilowatt peak PV system. And the aim of story, or the main objective, was to reduce the demand charge on the energy bill and show the combination of a storage unit and with PV integration. To fulfill that aim, a 200 kilowatt hour lithium-ion battery with 50 kilowatt power output has been installed. It should be noted that during the project duration, the regulation in Spain changed quite frequently. While they were not allowed in the beginning to inject any PV electricity into the grid, that changed throughout the project, so the charging strategy had to be adapted. In the end, they were not only able to inject PV into the grid, but also charge the battery from the grid. This leads to our 4 use cases, where use case 0 describes a case where it is only the factory, so there's no PV system installed and no battery installed either. Use case 1 is the actual reference case for this demonstration, where a PV system is installed. And use case 2 and use case 3 describe the case where a battery is added to the PV system. In use case 2, the battery cannot be charged from the grid, while in use case 3, the battery may be charged from the grid.
Johanna, what is the outcome of the environmental assessment?
So again, we did an environmental assessment using LCA for this demonstration case. This figure shows you the result on annual greenhouse gas emissions in tons CO2 equivalent per year for all three use cases. On the top, you see the first use case, 0, where no PV and no battery was installed. The dark blue bar for all use cases are the total emissions, and the other bars are the contributions to these total emissions. And for use case 0, the only contribution was the electricity the factory consumed from the grid. In this case, we used the Spanish electricity mix, and this added to approximately 100 tons CO2 equivalent per year. In use case 1, we investigated what happens if the PV is installed, or what is the benefit from the PV unit. And here we have additional greenhouse gas emissions in the life cycle assessment. We considered also the manufacturing of the whole PV unit, which is used in the factory. Again, we still need some electricity from the grid, as the PV unit is not covering the complete demand. But what we also included in our assessment is that at certain times we have a surplus PV production, which is again injected into the electricity grid. And there, this amount of injected electricity replaces a certain amount of or a certain type of other power generations. In this case, we investigated in a project different options, but here we see the results if we replace again the Spanish electricity mix with this amount of surplus PV electricity. And this was included in this assessment as it is a replacement with negative emissions. And if we add this together, we see that the implementation of the PV unit reduces the total greenhouse gas emissions by approximately 30%. And then we have the two cases with the battery, where the battery and the PV unit are investigated. So we have additional emissions. This is the orange bar from the battery manufacturing, which is a rather small share in the complete system. The battery leads to the situation that we can decrease the electricity demand from the grid a little bit. So greenhouse gas emissions from the grid are decreased, but we also decrease the electricity which is injected into the grid and replaces other power generation types. So in the end, again, due to the fact that we have a little bit more emissions from the battery manufacturing, and also the positive effects from having less electricity consumed from the grid, does not compensate for the storage losses. So we have a little bit more greenhouse gas emissions here. But as everybody knows who is working with LCA, we have a certain amount of uncertainties in these calculations, and 3 tons CO2 equivalent a year more is a really rather small increase in emissions. So you can say it's more or less the same. And yeah, in use case 3, we had the possibility to charge the battery also from the grid, which in the environmental assessment showed no difference in the result, because the amounts of energy investigated were very similar in use case 2 and 3. And the time of the electricity consumption and replacement was included in hourly emission factors in the calculations, but in the results we saw no difference. The electricity generation mix did not change on this from an emission in terms of emission factors on this timely basis. So there was no difference here. And on the next slide.
Thanks, Johanna, for the environmental impacts. We go to the economics.
Okay.
Okay, for the economic assessment, we mainly looked at demand charge reduction. where in the second row we see the case where there is only the load, so no PV system installed. The second load and PV system, and the last row shows the load, PV system, and the battery. And it is shown that for the winter months of January, February, and March, the introduction of a PV system does not really lead to any demand charge reduction. And this is due to the fact that in Spain, the high tariff period starts at 5 o'clock in the afternoon. So it does not really coincide with the PV generation. However, if we introduce storage, then we are able to shift the excess energy around midday into the high tariff periods in the afternoon, and can therefore average a reduction of around 6% in the demand charge. It changes a bit if we look at September and October, because in summer the high tariff period is from 10 to 5, so right in the PV generation time zone, and therefore the introduction of a PV system reduces the demand charge right away. The introduction of a battery in this case does not really make any sense, as it shifts the exceeding PV production into a flat period in the afternoon. In the diagram below, we see the energy charge, so the total energy bill over 1 year. And in blue, we see the bill if only loads are considered. The orange bar shows the introduction of PV, and it's shown that it's quite significant, the reduction if we introduce PV. The green one shows the introduction of a battery, and as you can see, this does not really influence the overall results.
So, what are the conclusions, Camilla, of this demo?
So in general, it can be said that the introduction of a PV system decreases the demand charge significantly, while in winter the battery plays an important role to shift the excess electricity into the high tariff periods. However, it should be noted that at the moment, in this use case, the battery does not provide a business case. However, the battery has often been unavailable due to technical issues. And also it can be said that the greenhouse gas emissions increased really slightly compared to the case where only PV is installed.
Thanks, Camilla. We have a fast look at two other demos.
Yeah, so the next demo we look at is a residential village of Suha in Slovenia, where they installed a community battery, a 320 kilowatt hour, 170 kilowatt lithium-ion battery. And we look at two different scenarios: a low rest scenario where 210 kilowatt peak PV are installed, and we have a use case without battery implementation and a use case with battery implementation. We also look at a high rest scenario due to expected grid issues at higher PV penetration levels of 630 kilowatt peak PV, and we consider the same use cases as mentioned before.
Okay, here you again see the results on the environmental assessment. The structure of the figure is the same as I explained before. On the top, we have the two use cases for the low PV scenario, and on the bottom for the high PV scenario. The main difference to the demonstration case before is that here we inject a higher amount of electricity into the grid, of surplus PV electricity into the grid. So this yellow bars, which represent the negative emissions from electricity, other types of electricity generation, have a higher influence on the total result, which are the dark blue bars. And for the use cases with low PV, we have the same thing as before, that the use case with battery has higher annual greenhouse gas emissions due to additional greenhouse gas emissions from battery manufacturing, but mainly due to storage losses, which influence the greenhouse gas emissions from electricity from the grid and the amount of greenhouse gas emissions which can be replaced, which are a lot smaller compared to use case 1. And this picture changes for the high-res scenario, where in the first use case, we really have PV curtailment, meaning that we have less PV electricity in the system, and implementing the battery enables more use of PV electricity. So in the use case 2, we have more PV electricity in the system, leading to two things. That one is that we need less electricity from the grid, so the gray bar is smaller. But on the other hand, we have more surplus PV electricity, which can be injected back into the grid and also has a positive effect on negative emissions. And here we have the case that the total greenhouse gas emissions for the system with the battery are smaller compared to the system without the battery.
Camilla, economics of this demo?
Yeah, so we also looked at the low res scenario, which are represented by the blue lines. And while in this scenario, basically no curtailment happens, the only use of the storage is for arbitrage in the light blue line. And it is shown that this does not create a business case. While in the dark blue line, we assume that the storage takes part on the reserve market and therefore generates revenues on this market. For the high-res scenario, the battery is primarily used for curtailment, and we also consider the case where part of the battery is used for curtailment while the other part of the battery is used on the reserve market. So for example, in spring, 60% is used for curtailment while the other 40% can be offered on the reserve market. We calculated with the current storage system price of 500 euro per kilowatt hour, and at this price, it does not yet provide a business case. However, this diagram shows really neatly that if storage costs drop to around 250, 300 euro per kilowatt hour, there would be a business case. This battery, however, also provides really interesting technical benefits to the grid. For example, the peak power changes at around 40% for the low-res scenario as well as for the high-res scenario in both positive and negative ways. And the grid losses can be reduced by 7% in the low-res scenario and by 21% in the high-res scenario. And also the grid, the local low voltage grid can consume 20% more locally produced energy. This could lead to infrastructure upgrades being delayed, for example, grid extensions for transformer into the new transformers. So this shows the technical impact a battery can have. In general, it can be said that this demo shows that for certain demonstration setups and use cases, the battery does provide a business case, for example, from the reserve market or in case of minimized curtailment. And it is also shown that in the case the battery minimizes curtailment, the environmental benefits are given in comparison to a reference case. It should also be noted that there are important technical benefits to the DSO, like peak demand reduction, reduction of losses, or increased local res generation.
Conclusionsfolie ganz hinten. Many thanks, Camilla. We have still one slide with the with the main conclusions. So after having zoomed into two demos and having seen the environmental effects, the technical effects, and the economic dimension, we draw the following conclusions. Storage needs to be tailored to specific issues it should solve. There's no argument for general large-scale storage rollout without any rationale behind it. We see different break-even points for economic and environmental benefits. There's the risk that you find business models and business cases that may not lead yet to environmental benefits. The energy system view is important. As Johanna already mentioned, she took in her environmental assessment a very broad energy system view. Some demos would be environmentally beneficial if you take only the small demo perspective, but if you embed it in the broader energy system, you have counterproductive effects. As long as the grid can act as a storage, it's environmentally more sound as a solution. And as we saw in the case of the community battery in Slovenia, renewable deployment can be supported with storage in a more indirect way by providing benefits to the DSO by delaying infrastructure reinforcement or improving power quality. Many thanks for listening. Now we are open to questions.
Thank you very much. Yes, hello. There are actually no questions yet from the audience.
Okay.
But we would like to ask the type of thermal storage used in the residential demo.
In the residential demo, we had seasonal underground storage. You mean the residential demo? It didn't work well. The heat was already gone. The summer heat was already gone in November. We installed a very innovative state of charge measurement systems, but we saw that these sensors were broken due to bad weather or cold weather, so it didn't work well.
Okay, thank you, Andreas. That was actually a question from me, because the next session there will be another workshop this time related to residential storage, and so indeed we have a few things with hybrid storage combining both thermal and electrical storage. So that's quite interesting to. It's very connected, I think, to this demo that you had in Belgium.
I still want to give one information to the audience. Due to time constraints, we skipped one of the demos, but in the material that will be uploaded, this assessment is also included.
Okay. Great. And I wanted to ask as well the technology readiness level that you managed to achieve. Again,
it's very difficult because you have a technology readiness level. If the project starts, it's based on your assumptions, but over such a long time span, your assumptions prove to be wrong. We saw that, for example, aggregating flexibilities in the residential sector is far not market ready. We have so many interoperability issues and problems. Or we saw that compressed air energy storage, we assumed it's TRL5, but it proved to be TRL4. Other solutions already maybe more market ready than we thought.
Okay.
But overall, the TRL levels are systematically lower than we assumed. So there is no clear plug-and-play storage system that you can immediately use and where you have no problems. You always have problems between the battery, the inverter. If you control and communicate, this raises issues. We have IT interoperability, but also we have interoperability issues between energy devices. So overall, lower market readiness as we assumed a couple of years ago.
Okay, clear, thank you. And we have a question, Zia, I see from the audience as well.
Okay, can you elaborate a little bit on your large-scale simulations? What was really done here?
Yeah, that we will go to the respective slides.
Well, the large-scale simulation was done by the colleagues from the University of Ljubljana. What they did was they implemented a certain type of electricity grid in a simulation platform and made a technical simulation based on 15 minutes or 5 minutes intervals for this grid, for typical days per season. So they picked a typical seasonal day and investigated a winter day, a spring day, a summer day, and a fall day. And it is, as you see on the right, it is they included a transformer between the high voltage and medium voltage level. This transformer had a peak power of 30 megawatts. And below that, they had two different types of feeders. The one was an urban type, and the other was a suburban feeder, going from the medium voltage then to the low voltage level. And there, on the low voltage level, they implemented certain type of loads where they included electricity demand from households as well as electricity demand from electric vehicles. And they implemented, this is the red and the green parts in the figure, they implemented existing low voltage grid sections from the Story project. So this is the green one is Suha, which is one of the demonstration cases. The other one was a grid section on an industrial site, and yes, so it's based on real grids, and they extended this to this synthetic network, which was investigated. But if you have more questions on that, we can send you a deliverable describing this in detail, for example.
Thanks, Joanna.
You have to unmute, Zia. You are muted.
Thanks. Sorry. Yeah, for any additional questions, you can email sustainableplaces@r2msolution.com, and we can make sure we connect those dots for you. So thanks from the audience. Thanks to the presenters. Very interesting project and presentation. At this time, we will shift over to the second and final presentation for this short session, coming from Adriano Sciacovelli. Hopefully I pronounced that better this time, from University of Birmingham. And he will be presenting kinetic modeling of thermochemical energy storage reactions for storage of solar heat. Take it away.
Thank you very much. Can you hear me? Just double check you can hear me.
Yes. If you can just put your slides into presentation mode.
Sure.
All set.
Absolutely. All right. Thank you very much for the introduction. Let me just put the presentation on. Thank you very much, everybody. Thank you for attending this presentation. My name is Adriano Sciacovelli, and I'm very glad to present this contribution from myself and my colleagues at the University of Birmingham. I'm one of the academics of the School of Chemical Engineering and member of the Birmingham Center for Energy Storage, which is a cross-campus initiative at the University of Birmingham. So we focus mostly on low carbon heating and cooling technologies with a focus on thermal storage, and hence the let's say the aim and the reason of this presentation. So let me just dive into the outline and into the objectives of this presentation. So I have really two purposes here in presenting this work. One is to present the context in which this work is unfolding, which is an Horizon 2020 project, which I will discuss in a little bit more in the next few slides, and to present the contribution of the University of Birmingham in this project. So the particularly focus here would be on the let's say behavior, kinetical behavior, in general thermodynamic behavior, if you prefer, of a low TRL thermal energy storage technology, or class of technology, which is called thermochemical energy storage, and present how this work actually contributes to the advancement of this European project that has been started 1.5 years ago. So let me first put a little bit of context on within which challenge we are actually trying to face in this project. So the project focuses largely on addressing one of the, let's say, hidden sources or resources that are available in the, let's say, in the energy system in general, which is the industrial waste heat and industrial also waste coal, and how to valorize these resource or this wasted energy, if you prefer, toward the carbonization of energy-intensive industries, as well as overall, let's say, EU heating. So, as you might be aware, this slide presents a high-level estimation that was carried out at the beginning of the project, which essentially shows that at aggregated level, the amount of wasted heat across heavy industries across Europe, if we take a simple, let's say, energy balance approach, would be sufficient to cover a significant portion of the EU heating. So this is a well-known challenge, and it has been, let's say, identified for several years. But the key challenge is to understand what to do and how to actually valorize these source of energy. So if I goes back to one slide, typically the assessment of waste heat is carried out at, let's say, regional or national level. So we know the total amount of energy that could be recovered. But when it comes to practically and technically try to recover that type of wasted energy, we face several steps from monitoring the amount of waste heat, design and select the technologies that are needed to recover it, and ultimately to maintenance and monitor the technologies that are eventually put in place to recover such waste heat. So what you see here is it's a schematic that shows how technically actually the recovery of waste heat will unfold, from identifying sources of waste heat. These are, for example, plants that are around the city of Birmingham, and within that plant, identify the necessary components and units where the waste heat occurs, and potentially identify how the fluctuation of this waste heat takes place over time, and then thread these with the potential heat demand or demand of heat or thermal energy in the proximity of the process or within the process itself. So it's necessary to thread all together these steps to actually valorize such source of waste heat or such amount of waste heat that is typically assessed just at high level. And here is where the, let's say, SOWOT project comes into play. So the SOWOT project is a project that involves 20 partners and 11 industrial demo sites. And it aims to develop an integrated software, an integrated modeling platform for auditing industrial processes, planning and simulation of waste heat and cold, valorization and technologies, and identify how these amount of waste heat can be economically recovered and economically exploited. So we are trying to, through the development of this platform, thread all those steps together that I mentioned before, and not just at the industrial process level, but also at the community level. So we are looking at, with this platform, to actually assess waste, valorize waste heat inside the process or on site, as well as potential transportation of this waste heat, or let's say a delivery of this waste heat in the communities around, within obviously the changing landscape of increased penetration of renewables also in industrial processes. So this is the context within which also the work of the University of Birmingham is fitting. So one of the, let's say, various technologies that we are addressing is thermal energy storage. And the key question that we're trying to address is how thermal energy storage, and in particular thermochemical storage as well, can facilitate the recovery of waste heat. So there are three essentially key barriers and aspects that we are addressing. The first one is, the first two are more, let's say, non-technical, and one is technical. So let me start from the technical one. Through this platform, in particularly around the role of storage, we are trying to make sure that, let's say, the perception of the technology and the use of technology is expanded compared to the current use of thermal storage. And in particular, we are looking at how storage can be coupled with other technologies for heat upgrade or heat to power recovery of waste heat, in a way that ultimately, when this information is embedded in the SOWOT platform, it will lower the uncertainties perceived by investors and by industrial stakeholders, so that they can go ahead confidently with investments in actual implementation of technologies in their processes to make them more efficient and to recover the waste heat and the waste coal that is potentially available. So this slide shows, let's say, the set of technologies that we are modeling inside the SOWOT platform. And in the box, you notice, let's say, one subcategory of these technologies, which is the thermal energy storage. And as I mentioned, we are looking at how, let's say, not just in isolation, thermal energy storage can support the waste heat and waste coal recovery, but how also hybrid solutions and the modeling of hybrid solutions can facilitate the recovery of waste heat and waste coal. So what I mean by hybrid solution is the coupling of thermal storage with other recovery technologies, and how these hybridization can actually make the overall recovery more feasible and more economically viable. We are looking at various, let's say, TRL levels. So one of the reasons, or one of the aims of this project from the technical point of view, is to make sure that on board in this modeling platform, we have both well-established technologies, or the end user will be able to model recovery options with well-established technologies, as well as with near-to-market technologies, or technologies that currently are low TRL level, but they might come up online later on, and therefore the user of this platform can have a competitive edge if he or she is able to address technology that will come up in a few years. So moving to the, let's say, more specific aspect of storage and on the thermochemical energy storage. So the options that we are looking and we are modeling in this platform, or that we are embedding in the overall platform, are, as I said, both on-site recovery or on-site storage of fluctuating sources of heat for process reintegration of such heat. But also, let's say, as a secondary option, we are looking at possible off-site options, where the heat that might be recovered from an industrial process is actually, so to say, shipped to nearby centers of heat demand or coal demand. And in this presentation, I'm focused just on the work of the modeling work that pertains the so-called thermochemical energy storage options. So thermochemical energy storage exploits essentially reversible reactions to store and then release heat. So at a high level, essentially, if there are suitable thermochemical reactions, reversible reactions, these reactions can be essentially shifted from one side to the other one, providing a certain amount of heat. So if we have two compounds, A, B, chemical compounds, I will show you some of the reactions that we are addressing. The forward reaction can be used to store heat and to produce separate compounds A and B, while the reversible reaction, when A and B are combined, these will release essentially the enthalpy of the reaction, and then essentially provide the discharge stage of the thermal storage technology, and will produce, let's say, the original form of the chemical compound. So obviously this is a quite, let's say, comprehensive and challenging to cover all these steps. So we are moving from the kinetic aspect of the reactions potentially to the techno-economics of these, let's say, thermal storage devices for multiple candidates and multiple operating conditions. So we have developed in this kinetic modeling framework, in our modeling framework for storage, an actual 6-step strategy that will be implemented inside the platform, the SOWOT platform. So this will be one of the modules of the platform, that will cover the thermal storage options, together with obviously all the other modules for the other technologies for the assessment. So typically, this platform will allow to, starting from obviously evaluating the sources of waste heat and cold, select the functional parameters of the storage options, so essentially the operational envelope, temperature level, pressure level, etc. Shortlisting the actual materials that are available within the operational envelope, moving to the techno-economic sizing and costing, and ultimately to the let's say simulation, the monitoring aspect, the simulation of performance in operation. And one of the key features of our work is that it is complemented with experimental data on the actual materials, so that the actual assessment is backed up by measured data of materials that are suitable for the thermal storage options. So I'll essentially present some of these steps, given that we are, let's say, at early stage in the project, so these are early on results about the development of this platform. So one of the initial steps, the early steps of the methodology that we have developed is the systematic screening of obviously the options available. Here I'm focusing only on the thermochemical storage options. So what you see on the left-hand side and on the right-hand side are two snapshots of the database that is available. Essentially, will be available in our SOWOT platform, where multiple reactions for different type of materials have been identified, as well as the temperature range within which these material options will be suitable. So the end users of the platform will be available to enter the let's say their inputs, identify the temperature ranges within which he intends or she intends to operate the storage, and then select or identify the suitable candidates. Obviously, here we are looking at a technology that is let's say low TRL, but as I said, we want to give the options to also explore potential technologies that are coming up. One of the key features of the thermochemical storage option that you notice here is that the actual temperature, the envelope of temperature conditions that can be operated within is variable and is essentially a function of the pressure at which the reaction takes place. So the thermochemical storage options allows to store heat, but also potentially to upgrade heat if a suitable pressure is selected. So moving to the next step, once the user will be or is able to let's say identify the material options, the user will be able to identify or to address the let's say hybridization of these thermal storage options with other technologies. As I mentioned, we are looking for combined and synergies effect among various waste heat recovery technologies. So what we see in this slide, it's let's say graphical interface, if you prefer, of how the candidate reactions that I mentioned before fits or suits other the operational conditions of other waste heat recovery technologies. So just to give you an idea, on the column here, we have consider, let's say, low temperature organic Rankine cycle waste heat recovery technologies, and the let's say color map allows the user to identify which best combination of thermochemical storage and waste heat recovery technology could be exploited. And as you see, essentially in certain areas there are pairs of technologies and thermochemical storage reaction which, due to thermodynamic conditions, do not match well. While others, there are actually opportunities to let's say integration of these technologies for a quite broad temperature range. Where the map here, the color map, relates to the temperature at which the storage and the recovery of heat is potentially taking place. So at this stage, the user will be able to identify eventual synergies and go ahead to assess them in more detail in the platform. And as I said, we want to make sure that also the dynamic aspects are taken into account, and that the performance of the thermochemical storage options are backed up by experimental data. We focus the experimental analysis only, let's say, on the most, let's say, explore or establish thermochemical storage options, not necessarily all the reactions that you mentioned, but that I mentioned in the previous slide. This gives you an idea with, let's say, a case study, which is magnesium chloride, which is a thermochemical storage material, a salt hydrate for relatively low temperature thermal storage, let's say around 100, 150 degrees C, where at our laboratories, we are extracting from experimental data, essentially from thermogravimetric analysis, the models for the kinetics of such materials. So what you see here, it's a typical dynamic vapor sorption analysis, or let's say kinetics or uptake of water by these hydrated salts. And on the left-hand side, you see a reconstruction of such kinetic on slightly different format with an integral method here. And this reconstruction allows us to essentially parameterize and have a mathematical formulation of the kinetics that will be used to model the dynamic behavior of material in a thermochemical storage device within the SOLVE platform. Obviously, the user, as I will show you later, will have a, let's say, user-friendly interface, and this type of data and analysis will be, let's say, the back engine of the platform. But we want to make sure that this is taken into account properly, and hence this coupling between, let's say, modeling and experimental characterization. So this is again one of the, let's say, results or options that the user will be able to address or to investigate. So one of the key aspects, as let's say identified also by the title of this talk, is that there is a variety of approaches with which we can model the kinetics of these thermochemical storage options and materials. Or in other words, there are multiple kinetic models that in principle can be used to model how the reaction progresses. And what you see here in this chart is a statistical analysis of the prediction of the kinetic models against the essentially experimental data. So on the horizontal axis, these labels identify different kinetic models, and basically the R-squared statistical indicator identifies how good these models are able to replicate the kinetics of the salts that I mentioned before, or in general the thermochemical storage options that I mentioned before. So this is again to give the confidence that the results are robust, but also that are backed up by these experimental evidences. So ultimately, in the platform, and the user will probably start and begin to analyze his or her process with potential storage option integrated into it to recover waste heat, or to deal with fluctuating sources of heat from solar, for example, as well. But let's say the data flow and the workflow of the platform will allow to replicate the kinetic behavior of such option that the user is selecting. This kinetic behavior is fed into a, let's say, computationally inexpensive model of the actual storage device, storage reactor. So here we have a lump parameter type of models where we bring in the kinetics that was previously reconstructed, and ultimately the user will have a user interface where the storage option will be confronted against a series of KPI, or key performance indicators, to identify, to, let's say, support the decision of the user in potentially integrating in his or her process a storage technology to improve the recovery of heat or waste heat. So again, using the magnesium chloride as a case study, I'll give you a glimpse on how this interface will look like. So on this will be a typical, let's say, chart or output, graphical output that a potential user will obtain selecting one of these thermochemical storage options, where you notice various, let's say, techno-economic performance indicators, starting from, let's say, energy storage density, cost per unit of stored energy, but also aspects that relates to the dynamic behavior of the storage option, like power density and let's say time necessary to ramp up the storage system, so the dynamics, while the internal chart presents the predictions that are obtained with different kinetic models. So as you notice here, there are 3 kinetic models. Here are essentially a linear driving force model and a diffusion-based model, and how these performance or how these key performance indicators are affected by the selection of these kinetic models. And similarly on the right-hand side for potentially other salts or other thermochemical storage materials, as well as other reaction mechanism and kinetic models. So this brings me to let's say the conclusion of the last slide about contribution of this work and of this ongoing activity, which are 3 in essence. So a rigorous framework for supporting decision making in selection of thermochemical storage options in the context of fluctuating heat sources, waste heat, or potential also renewable heat. A 6-step procedure is has been developed and will guide the user and the stakeholder using this SOWOT platform. And this platform or this 6-step procedure is generalized to cover sufficient large options of thermochemical storage materials. I just want to mention as one last point that in the next few months, if you will check the website of the project, there will be a free version of this platform. It will be an online-based platform where, let's say, some of the functionality will be publicly made available. And this brings me to the conclusion, and I'll thank you for your attention and hand it back to the chairperson of this session. Thank you very much.
Thank you, Adriano. Very interesting. There are no questions from the audience, but I would also like to ask you the same question in terms of expected TRL or phase of commercialization for the full-scale platform.
Yeah. So the platform itself will be commercialized by one of the one of the partners of the software developer. So there will be a commercial product for the platform itself. Within the platform, the technological options that will be covered by the platform go from TRL 5 to 9, essentially. So this relates to the previous one of the previous charts and tables, where we have about 40 technologies, waste heat recovery technologies within the platform. Thermal storage is just one, but we wanted to include both market available options as well as, let's say, near to market, to also basically leverage results and interesting findings from ongoing and previous European projects.
Wow, that's ambitious. TRL 5 to 9. Good luck.
It was actually stated in the call itself.
Okay, great. Well, keep us posted. Hopefully next year for Sustainable Places in Milan, you can give us an update.
Absolutely.
All right. Well, yeah, there's no questions from the audience. So at this time, I think I'll just close this session with a big thanks to both of our contributors. And again, if there's any questions or follow-ups from anybody, please feel free to email us at sustainableplaces@r2msolution.com. Also, I'd like to point out that the next session on this track, starting at 11 o'clock Central Eastern Time, is integrated storage for residential buildings. And it's a workshop, so it'll be similar and interactive. So please, everyone, feel free to join in and enjoy the rest of your conference. Thanks very much.
Thank you. Bye-bye.
Bye.
Bye.